Hi everyone, this is Sunita, Assistant Professor in EC Department, Siddhartha Academy of Higher Education, deemed to be University. In this class, we will see semiconductors and formation of the PN junction. So, what is the purpose we need to know the semiconductors? Why we need to know about the semiconductors? Nowadays, everyone life depends upon the electronics. The world deeply depend on the electronics. Can we imagine our day or 2 or 3 hours without our mobile? What is the relation between the semiconductors and the mobile? The mobile is fabricated by the chip. We all know the chip. The chip is nothing but integrated circuit. The integrated circuit are fabricated by the interconnection of the millions of transistors. The transistor is nothing but fabricated by the back-to-back connection of the diodes. Depending upon the application, the number of the transistors and the chips may be vary. So the diodes is nothing but formation of the semiconducting materials. So the basic layer of the electronics are materials are semiconducting materials. So in this class we will see what are the uh, materials classified by their ability of charge carriers and what are the types of the semiconductors and how we can form the PN junction. The classification of materials. The classification means anything in any way. The classification means depending upon the one property. Based on the one property, we can classify. Like that, based on the ability of the conduction. The ability of the conduction, the materials are classified into conductors, insulators, and semiconductors. So, we can classify those materials using the bands in the solids. In solid materials, electron energy levels from band of allowed energies are separated by the forbidden bands. So in valency band, the outermost, the highest band, all states are occupied, filled. In conduction band, the next level of the band, highest band, valency band, empty or partial band. Energy difference between the valency band and conduction band is equal to the forbidden gap. So the insulators, conductors and semiconductors classified based on the forbidden gap. See here, insulators. In insulators, the conduction band, valency band, the energy gap between the conduction band and valency band is approximately equal to 6 electron volts. It is highly impossible to apply that much of energy to move the charge carriers from valency band to conduction band. That's what insulators are unable to flow the charge carriers. When coming to the conductors, see here, the conduction band is up to here and the valency band is up to here. That means there is no energy gap, there is no forbidden gap between the conduction band and valency band in the conductors. That means there is a chance completely move of charge carriers across. There is no need applied any force to conduction of electrons. When coming to the semiconductors, in semiconductors, the conduction band, and this is the valency band, the electron gap, the energy gap is approximately equal to 1 electron volt. That means we can apply, if you apply energy greater than 1 electron volt, there is a chance of the conduction. Why we need semiconductors? That means we have the conductors which allows the charge carriers. Then why we need the semiconductors? That means in conductors there is no controlling. There is no control. The band gaps are overlapped. But in semiconductors, we can control the flow of the charge carriers by the applied field. Semiconductor electronic materials. The goal of the electronic materials is to generate and control the flow of the electrical current. That means in semiconductor only we have the property of the control. In conductors, we are unable to control the charge carriers because the both energy conduction band and the valency band overlap. Conductors have the low resistance, which allows the electrical current flow. Insulators have the high resistance, which suppresses the electrical flow. The semiconductors can allow or suppress the electrical current flow depending upon our applied force. Semiconductors are classified into two types, intrinsic and extrinsic. Intrinsic means pure semiconductors. The nature available semiconductors are pure semiconductors. Example, germanium and silicon. The fourth group elements, which has the 4 valency electrons in the outermost shell. Germanium, silicon are the nature available pure semiconductor materials. The pure materials are called as the intrinsic semiconductors. So the impure, that means if any materials added to the pure semiconductors, that are called the extrinsic semiconductors. Again, what are the impurities were added to the pure semiconductor? Based on that, the extrinsic semiconductor again classified into two types, N type and the P type. So doping, to make the semiconducting conduct electricity or to increase the conductivity of the semiconductor. In pure semiconductor, the conductivity is low. To increase the conductivity of the semiconductor, we are going to adding some more elements, extra elements to the pure semiconductor that result in extrinsic semiconductor. So the process is called the doping. Depending upon the type of the doping material we are using, the extrinsic semiconductor can be classified into two types, N-type semiconductors and the P-type semiconductors. Here, the N-type extrinsic semiconductors. This type of semiconductor is obtained when a pentavalent element like antimony. Pentavalent means the outermost shell has the 5 valency electrons, fifth group elements. Those elements added to the fourth group elements, that means the pure semiconductor materials, germanium or silicon, is added to the then what will happen? The dopant has the 5 valence electrons, 4 valence electrons used for the covalent bonds surrounding the silicon atoms. Each antimony atom forms the covalent bonds with the surrounding 4 silicon atoms with the help of the 5 valence electrons. See, it can be easily excited from the valency band to conduction band. That means silicon has 4 valency electrons, antimony has the 5 valency electrons. The 4 valency electrons, pure silicon, and the dopant 4 valence electrons can form the covalent bond, and the dopant has the one excess electron. This electron can easily move from valency band to conduction band. The resultant is known as the N-type. That means the excess elements are electrons. The excess elements are electrons. So it says from the above description that N-type semiconductors electrons are the majority charge carriers. Dopant examples are phosphorus, arsen. So when we will get P-type extrinsic semiconductors means if the pure semiconductors, germanium or silicon, added by the trivalent element, that means 3 valency electrons, third group elements, then what will happen? Third group element examples are boron, aluminum, gallium, indium, like that. The dopant has the only 3 electrons. The silicon has the 4 electrons. The 3 electrons in the dopant, 3 electrons in the silicon has formed the covalent bonds. There is a one space, lack of electron, the absence of electron in the covalent bond. So the absence of electron is called the hole. In this, see, N-type semiconductor and N-type semiconductor. Here the fifth group element, formation of the covalent bonds, all the black dots, and this fifth group ion, fifth group element. This fifth group element, the valence electrons of 4 form covalent bonds with the germanium. These blocks are silicon, pure semiconductor. This blue dot is the fifth group element. It has the one excess electron. One excess electron. These electron can easily move from valency band to conduction band to construct electric flow. So then excess. So electron has the excess. Majority charge carriers here are electrons. So this is the n-type semiconductor. Coming to this one, p-type semiconductor, trivalent impurities added like boron, aluminum, gallium, like that. So these black are silicon atoms. This is boron atom. It has a third group element. It has only 3 valency electrons. Here the 3 valency electrons form the 3 valence electrons of the silicon in covalent bond. This is the fourth valence electron of the silicon. Here we need one more electron. That means absence of electron. Absence of electron, absence of negative charge is called the positive charge. Absence of electron is called the hole. There is a formation of the hole. So in p-type semiconductor, charge carriers are hole. In n-type semiconductor, charge carriers are electrons. This is about the how the p-type and n-type semiconductors form from the pure semiconductors. So what will happen when p-type and n-type materials just form? So till now we have seen what are the materials classified based on the charge carriers flow, conductors, insulators and semiconductors, and what is the need of semiconductors, and what are the pure semiconductors, and how we will get the uh, p-type and n-type semiconductors, and why we need to add the impurities to the pure semiconductors. That means to increase the conductivity of the semiconducting materials, we are going to add the impurities to the pure semiconductors. That process is called the doping. If you dope trivalent impurities, or we can dope pentavalent impurities. If you dope pentavalent impurities, we will get the n-type semiconductor. If you dope trivalent impurities, we can get the p-type semiconductors. Till now we know this. So what will happen when we attach, we join, just we took nearby p and n-type materials. Okay, now see here, this is the p-type material, this is the n-type material. We know that p-type material has the highest charge carriers, majority charge carriers are holes. In n-type material, majority charge carriers are electrons. See here, this is the junction. This is the formation of the junction, P and N junction. All these circles indicate the holes. These green lines indicates the electrons, free electrons. So these are the ions. Ion means immobile ions, negative ions. This red mark is indicates the positive ions. Electrons, majority charge carriers in n-type. Holes, majority charge carriers in p-type. Negative ions, positive ions. Whenever p-type and n-type materials are attached, we know that opposite charge carriers are attracted. So see here, the holes at the junction will come attract towards the electrons in the n-type and combine. At the same time, the electrons in n-type will attract towards the holes in p-type, because holes has the positive charge, electrons has the negative charge. So these electrons will move towards across the junction and combine with the holes and formation of the immobile negative ion. The holes in the p-type will move towards the n-type material and will form immobile positive ions. These immobile ions will create depletion region. Depletion means lack of charge carriers. At the same time, these depletion region opposes the further flow of the charge carriers from electrons from n side to p side, holes from p side to n side. So this is called the depletion region, also called as the electrostatic field. See here, in the p type, these are the blue circles are holes. In n type, the red circles are ions, doped ions. These electrons cross the junction and combine with the holes, the formation of the ions, immobile ions. At the same time, see here, the holes will flow from p type to n type and combine with the electrons and formation of the positive ions. So this is the lack of charge carriers. See here, there are no charge carriers in this space. Depletion region. The region has a depleted from the charge carriers. This is the very important thing we need to understand. This will useful further operation of the how PN junction diode operation, and at the same time, if you know the PN junction diode operation, then only we can know the transistor operation. After that, everything is depends upon the PN junction diode operation, how the current flow through the diode, and everything we will know if you understand the exact the concept of the depletion region. So this depletion region restricts further flow. That means there is a lot of gap. These electrons in n type unable to get that much of energy to cross this depletion layer and to enter the p region. At the same time, the holes in the p type unable, there is no that much of force. That means the open circuited, we just combine p type and n type, that we did not apply any external force. Just these electrons, these holes unable to cross the depletion layer to enter the n type to constitute the current. That means whenever we just formation of the PN junction diode open bias, we did not connect anything and we did not apply any external force. There is no flow of the charge carriers because there is a formation of the depletion layer. This region restricts the further flow of the electrons from N to P side, holes from P to N side. This is the concept. What will happen when P type and N type materials just form? There is a formation of the depletion region. This region restricts the further flow of the electrons from N to P and P to N. Then how we can able to this PN junction this material to conduct? So easy. The answer is very easy. If you apply the force to P side and N side, if you want to move the electrons from N to P, if you apply the force to electrons which is greater than the depletion layer width, if you apply the force to the electrons which is greater than the width of the depletion layer, that means the barrier and the potential developed in the depletion layer, if you apply the potential which is greater than the depletion layer potential, then electrons will move from N to P. Likewise, if you apply the external field to the holes greater than the potential developed at the depletion layer, so holes can easily move from P to N. There is a chance of the flow charge carriers constitute of the current. So till now we have seen what are the materials and depending upon the electric charge carriers, and how the energy bands difference in conductors, insulators and semiconductors, and how we can form extrinsic semiconductors from the pure semiconductors, and what will happen when P and N type materials are joined. So in the next class we will see the biasing. So now we told that I told that by applying the external field. So how we can apply that field, that is called the biasing. So we will see the forward bias and negative bias and open circuited, like that everything, and what is the relation between the current and the voltage in the PN junction diode. Thank you.